Welcome to my classroom. In this video, I will talk about matrices. Matrices is a topic of M2 in DSE syllabus, which is a half of the topic matrices studied in A-level pure math. The part taken away from pure math is transformations in R2. The geometric interpretation of matrices, which I think is good to learn, and thus have a better idea of matrices so that more applications can be taken place. So, the theme of this video is matrices on transformations in R2, and this video is to enrich the study of M2 in DSE. In M2 of DSE, the algebraic part of matrix is studied. We learn the definitions of matrix, the arithmetic operation between two matrices like addition, subtraction, multiplication with a scalar, and multiplication between two matrices, and some basic properties of matrices as well. We do not have division between two matrices, yet we have a similar form in terms of inverse. Just like the division between two numbers, if the divisor is 0, the division is undefined. For matrix, if the determinant of a matrix is 0, the inverse of the matrix does not exist. For those square matrices where the determinants are non-zero, we learn how to find their inverse. By multiplying the inverse, we have the equivalent result of division. For example, for numbers, is equivalent to, for matrices, is equivalent to. For multiplication between two matrices, it involves lots of calculation, particularly when the matrices are order 3. If we want to find a higher power of a matrix, the clumsy calculation is likely leading to careless mistakes. Fortunately, if we can decompose the matrix into the form of QDQ inverse, where D is a diagonal matrix, then the nth power of P can be obtained relatively easy by. Here, the power of diagonal matrix can be easily done by taking the power of entries in the diagonal. The working can be done by multiplying 3 matrices only. The way of the composition of matrix into a product in the form of QDQ inverse involves the ideas of eigenvalues and eigenvectors. I will talk about the way of finding eigenvalues and eigenvectors and their geometric interpretation in the next video. In the one after the next video, I will talk about drawing a firm by computer program, and the underlying ideas comes from some simple transformations by matrices. Let us learn the basic transformations with matrices in this video first. Suppose we are given a rectangle ABCD. Under a transformation T, the rectangle is mapped to A', B', C', and D'. In this video, we use X', Y' to denote the image of XY under the transformation T. That is, we are going to use matrices to represent various kinds of transformations, including rotation, refraction, scaling, shearing, translation, and their composition. Let us consider a feature of some common transformations. This feature is called linear transformation. Here is the definition. T map R2 to R2 is said to be a linear transformation if, for any points xy in R2 and real values as alpha, beta. That means the scalar alpha, beta can be taken out from the transformations without changing the results. With this definition, we have the following properties for linear transformation. 1. A linear transformation maps the origin to the origin. This property can be easily checked by taking x equals y equals 0 and alpha equals beta equals 1. Then, we have t of 0 equals 0. That is, a linear transformation maps 0 to 0. Note, here x and y are points in R2. 2. A linear transformation in R2 is represented by a square matrix of order 2. For any point in R2, say xy. Note that here x and y are real numbers and they form a point in R2. Regard the point xy as a linear combination of the units 1, 0 and 0, 1. That is, then the image under T is, by the definition of linear transformation, we have, therefore, to find the image of any points in R2 under T, it is equivalent to find the images of 1, 0 and 0, 1 under T. Let 1, 0 be mapped to AB and 0, 1 mapped to CD under T. That is, therefore, by multiplication, we see that T is a square matrix. In other words, if T is a linear transformation in R2, then T is where AB and CD are the images of 1, 0 and 0, 1 under T respectively. Conversely, a square matrix of order 2 refers to a linear transformation in R2. The checking of this statement is left to you as an exercise. 3. A linear transformation in R2 maps a line to a line. To show this, let T and L. Suppose xy is a point on L. The image under T is given by. We want to show x prime and y prime satisfy a linear equation. Firstly, make xy the subject by multiplying the inverse of the matrix to both sides. Use delta to represent the determinant. Then, substitute the result into the given line. Rearrange and simplify. We have, thus, x prime, y prime satisfy a linear equation. That is, they refer to a point on a straight line. Let T be the rotation about the origin through an angle theta anti-clockwise. According to the previous discussion, the images of the units on the x-axis and y-axis, that is 1, 0 and 0, 1, help to define the transformation. Referring to the diagram, by rotation, 1, 0 is mapped to cosine theta, sine theta, and 0, 1 mapped to negative sine theta, cosine theta. That is, therefore, in other words, let me use two simple examples to illustrate the working with matrices. The first example is to find the image of a point under rotation. It is easy, just apply the above result directly. That is, the image of 2 and negative 3 is. The second example is to find the image of a line under rotation. First, find the image of a point under rotation. Express x and y in terms of x prime and y prime. Put them into the equation of the given line. That is, the image is the vertical line given by x equals to negative 1 over root 2. Let T be the reflection about the line y equals to tangent theta x. Like the previous discussion, refer to the diagram. We have 1, 0 is mapped to x1, y1, that is cosine 2 theta, sine 2 theta, and 0, 1 mapped to x2, y2. In the diagram, the angle after adjustment is negative of pi over 2 minus 2 theta. Thus, the image is sine 2 theta, negative cosine 2 theta. Therefore, T is, and T of xy is. Here are some special cases under rotation and refraction. Rotation through 0 degrees is an identity matrix. Refraction about the x-axis, refraction about the y-axis, refraction about y equals x, refraction about y equals to negative x. For these simple matrices, we can see their geometric transformations represent. Let T be the scaling with factors h on the x-axis and k on the y-axis, where both h and k are non-zero. Referring to the diagram, we see that 1, 0 is mapped to h0 and 0, 1 mapped to 0k. That is, T of 1, 0 is h0 and T of 0, 1 is 0k. Therefore, T is. If G is a figure in R2 and G prime is the image of G under T, then G prime and G are similar if the two scaling factors are equal, and area of G prime is HK times area of G. There are two directions for shearing. 1. Shearing parallel to the x-axis with factor h. Referring to the diagram, 1, 0 is mapped to 1, 0, and 0, 1 mapped to h1 under this shearing. That is, therefore, T is an upper triangular matrix and the x-axis is the invariant line. That means the points on the x-axis are unchanged under this transformation. 2. Shearing parallel to the y-axis with factor k. In the diagram, 1, 0 is mapped to 1k and 0, 1 mapped to 0, 1 under this shearing. That is, therefore, T is a lower triangular matrix and the y-axis is the invariant line. Note that G prime and G are not similar, but the area of G prime equals to the area of G. Let T be the translation moving the origin to AB. For general point xy on the plane, xy is mapped to x plus a, y plus b under the translation. That is, unlike the previous transformations which are represented by a square matrix and thus a linear transformation, translation is not linear, as T of 0 is not 0. Let A be a matrix of rotations through alpha about the origin, and B be the matrix of refraction in the line y equals to tangent beta x. Then the product of matrix BA represents the rotation followed by refraction. We have BA refers to a refraction about the line where the angle is 2 beta minus alpha over 2, and AB refers to a refraction about the line where the angle is alpha plus 2 beta over 2. The lines of refraction are different, that is, the order of the composition matters. That is what we learn from multiplication of two matrices. We cannot swap the order of multiplication, otherwise we get different result. Now, let us consider the following example. The transformation is given by a system of equations. Rewrite the system in matrix form so that the transformation can be understood geometrically. Use the matrix form to represent the system of equations. We have, by setting cosine theta equals 0 and sine theta equals -1, we have theta equals to -90 degrees. Therefore, x prime y prime equals. The transformation is a rotation about the origin through -90 degrees or 90 degrees clockwise, and followed by a translation moving the origin to 2, 4. In general, a transformation in R2 has the following form. For some 2 by 2 matrix M and 2 by 1 matrix N, where M is a rotation, refraction, scaling, shearing, or decomposition, and N is a translation. Non-standard rotation refers to a rotation where the center of rotation is not the origin. Suppose a point xy is rotated about the point AB through an angle theta to its image x prime y prime. We can interpret this rotation as, first, take the translation by moving AB to the origin, then Do the standard rotation at the origin through theta, and then take the translation again by moving the origin back to AB. That is, let me use an example to show how a non-standard rotation works and how to identify the center and angle of rotation. Let the angle of rotation be theta and the center of the rotation be AB. Then we can link up the points A, B, C and their images like this. There are three unknowns, theta, A, and B. There are three matrix equations giving 6 equations in 3 unknowns. We may just consider the first 2 matrix equations. By subtraction, we have, compare the corresponding entries we have. Thus, theta is 270 degrees. Substitute back to the first matrix equation. We have, solve them. A equals 0 and B equals to -2. Therefore, R is, in other words, we have the center of rotation, which is 0, -2, and the angle of rotation is 270 degrees. In fact, the center of rotation can be found geometrically. Since the center lies on the perpendicular bisector of the line segment connecting the point and its image. Therefore, the center of rotation is the intersection of the perpendicular bisectors formed by AA' and BB', which is 0, -2, same as the one from the matrix calculation. Here are some exercises to consolidate your understanding of non-standard transformations. Answers are given for your reference.